Hello, Mr. Harry, Mr. Ryan, all right? Okay, we have been talking about Tic-Tac-Toe for 2 days, yeah, but we haven't talked about actually the strategy to play a Tic-Tac-Toe game, you know, as a computer, right? So we human, as a human, how do you play the Tic-Tac-Toe? Come on, if you want to play, what's your strategy?
If you get to pick
Okay,
the
so
first,
now,
you put the middle.
okay, so the agent is we talk about this, the agent, and then the cross is the opponent, okay?
No, wait. So like if the agent gets to go first.
Yeah, agent first.
You put it in the middle. Yeah.
Okay, so first
You
thing.
have the most possibilities to win.
Okay, so yeah, put the middle, and then what's next? Okay, so what's your strategy, Ryan?
And then the opponent either only can put around the
Yeah, okay.
but it doesn't really actually matter.
Okay, so then pick one. Come on, it's like you playing left hand with the right hand. Okay, now you playing the cross. So what are you going to put here? Anywhere. There's actually a big difference. Okay, look, there's only one center. It's like a little bit cute. You have one center, but look, this is in the middle. This is the corner. So which one you prefer, the corner or the middle?
I put middle.
Middle?
Middle.
You sure? Not the corner?
Corner.
Corner is better, right? Because look, you have 2 chances of winning here, but with the cross, remember we are playing the opponent here. You only have one, right? Because this one is already blocked, right? It's not possible for this to win. But if I put it here, I might have two possibilities in the future. If I put it in the middle, I only have one possibility, right?
Okay, but
Yeah?
the thing is, I don't really like to win. The thing is, I just don't want the opponent to win.
Okay, that's a very interesting thought. You don't want the opponent to win. You don't like to win, but you just don't like the opponent to win.
Yes, but I don't.
Okay.
Yeah.
So that's kind of strategy. Yes. But that would talk. If you don't want the opponent to win, that means that you need to win sometimes.
Yeah.
Yeah.
And the thing is, I don't really I ideally go with winning. I normally focused on the opponent's
Well done. Okay. Yeah. That's very good. That's very creative. Yeah, that's good. Okay. So I understand. Okay. So now there are 2 strategies. Yeah. So first of all is to occupy the center because that gives us more flexibility in the future. For example, if we put it in the middle, then we have we have how many choices? 1, 2, 3, 4. 4 choices. Yeah. 4 possibilities in the future. Okay, so as the opponent, then I will occupy the corner because that gives us more choice. Okay, what's next? Your cross, you're playing the agent. What's next? Ryan, what would you put the cross? What would you put?
I would put it on down.
Yeah? Which one?
I would put it in.
Where? Wait, which one? Here? Or here? Or here? You only have 1, 2, 3, 4, 5, 6, 7 choices. Pick one, come on.
I put it in the bottom left corner.
Okay, why is that?
Because you also have a chance of winning, but you're also blocking one.
Well done. Okay, so that's very good. So here we have 2 choices of winning, and we are blocking this one, right? Okay.
Yeah.
Okay, and then what's next? The cross.
You put it in the top right corner because. Why not?
Yeah, because look, if I don't put it, then I will lose.
Yeah.
Right? That's very obvious. Okay, and then I'll cross.
You put it in the top.
Yeah. Again, if I don't put it there, then I will lose. Right?
Yeah.
Okay, and then obviously it is here, right?
Yeah.
If I don't put it, lose. And what's next?
I'll put it in the left.
Yeah.
No, right.
Why is that? Why this one over this one?
Because you have like you can but if you put it here there is like no point because they can win. But
Oh, there, yeah.
But if you put it here, you also blocking it.
That's right.
Rather than just
Okay.
collecting.
And then which one is there? It doesn't matter, right? It doesn't matter at this point because you will have to block it, otherwise you'll lose. Okay. And then so you see.
Is it draw?
Yeah. You see for this game, Tic-Tac-Toe game,
Yeah.
left hand, right hand, yeah.
Yeah.
if we play smart, intelligently, the best result you can get is the draw. If you play with the computer, it's always a draw. Yeah? There's no chance you can win the computer. Because this game is so small, and then the possibilities, the number of possibilities we can just compute. Yeah? How many possibilities for this state? If we are talking about the state, there are how many squares are there? How many squares?
9.
9 squares. Okay, for 9 squares, each one, how many possibilities do we have for this one?
1, 2, 3.
How many possibilities for occupy the state of each square? How many state? How many state? The cross, the circle, and occupy. So there are 3 states for each one. So how many states are there for the Tic-Tac-Toe? Come on, each one has 3 possibilities. So there are 9 of them. So what's the total number of states? How many? 3,
Yeah.
3, 3. So I multiply
7.
3 to the power of 9, right? Because each one I have 3 possibilities. Cross, circle, and unoccupied. So the number of the states is 3 to the power of 9. This is actually a very small number, okay? I don't know, but it's a very small number. Is it? What's the power of 3 to the power of 9? Okay, let me just calculate it. What's the power of 3 to the 9? Huh? What's the power of 3 to the 9? 3 to the 9 is 19683. Okay, so it's 19683. Yeah, this is the total number of states. Yeah, so look, this is so small that we can just use the computer to prove forcing it. Okay, yeah, yeah, we can just try each possibilities, and I know that's why this game is. I mean, the best you can get is a draw. Okay, so to sum up, the strategy you follow is what? Okay, so let me write it down. Okay, so first of all, we prefer the middle. Eric, prefer the middle. If there is a center available, we prefer the center. Okay. The next one is what? Okay, so the next one is what? If the opponent is winning, if the opponent next winning is by placing us, in the slot, then we need to occupy that one, right? Yeah. So if opponent is winning, okay. The thing is that look. So we probably should move the second root to the first root, right? Right. Why is that? Look, if the thing is that. Okay. So if the thing is that. Okay. So now. Would you prefer the center or here? Yeah, so you obviously prefer here, yeah?
Wait, who am I? The circle of...
If it is cross, your cross you prefer here, right?
Yeah.
But if your circle, you also prefer here, right? Oh no, a circle you prefer here, right?
Yeah.
Okay.
If we get to
So
do it
look,
further.
so you see, these rules is not always true, right? There's an exception, am I right? Yeah, there's an exception. So this is called the rules. So we can implement these rules. This is kind of strategy that we can implement. That we can implement the strategy as a bunch of rules. So how does that work? So look, we can say, okay, this is a tree. This is a decision tree. We call it decision tree. Okay, so when you're now, then we can say, okay, is center available? Is center available? Available. If yes, then go play the center. Go place the center. If not, then okay, then we place in the center, place center, and then the end. Okay, the end. If not, then we can say, okay, is corner available? Right? If yes, then we place in the corner and end. Otherwise, continue. So this is kind of like the graph, the graph for you to implement the strategy, right? So we just check each condition, and if yes, we do this corresponding action, right? We talk about the actions, yeah? This is one kind of thing. Okay, so now this is okay if the search state is small. It's a search state is small and not complicated. But if the chessboard, yeah? If a chessboard, there are different pieces, yeah? The chess. chess is A times A, right? Yeah, and then there are few pieces, yeah, many pieces. So the number of states is bigger, a lot bigger than the tic-tac-toe. For the tic-tac-toe, we only have two pieces. But for the chess, how many pieces? We have a king, we have the queen, we have thrones, etc. I don't know, there may be 8, yeah. Look, and then it's on a A times A board. Okay, so I don't know if if there are 8 pieces, then each one has 8 states, yeah, including the unoccupied, that will be 9. Let's say 9. So 9 times what? 9 times 9 to the power of 64. So that's a very big number, which we can't brute force, right? Because this number is so big that even using the latest computer, we can't just exhaustive search everything, every possible situation, right? Am I right? Yeah. So we certainly need a more intelligent algorithm. Okay. So how can we represent these state in the search? So I show you. We will talk about the game tree. What does that mean? The game tree. Okay. The game tree. Okay. So at the beginning, we are here. So we have an empty board. Yeah, empty board. Yeah. Now, okay, so now the first layer is cross. So for cross, how many possibilities are there? Come on. Look, this is the starting point, 9. Okay, so I could place here. Look, I could place here, right? I could place here, etc. Okay, you got what I mean. Okay, and once this game board cross is picking here, so what's the next? The cross. So where can I put the cross? I'll put a circle. These available slot, right? So if I put it here, then the game will become what? Yeah. I could place here, so it will become what? Here, etc. Yeah, you see what I mean? Yeah. Yeah. Okay. So these will go on. So this one on the first layer, the cross. The second layer, the next layer, the next turn, circle, and the next turn, cross, etc. So each player takes turn. Okay. Yeah. Each player takes turn. Okay. So now, how do we evaluate the state? Right? How do we evaluate? So at some point here, look, if we go here, and if after the depth is 9, look, because there are only at most 9, yeah? 9 slots. Here, look, if it's somewhere here, can you tell me, what should I give it to? Who is winning? Who is winning here? Who is winning? X winning, okay? X is agent, yeah? And then this is opponent. Okay, we talk about when X is winning, the utility function will give a infinity. When this is winning, we give it negative infinity. When this is a draw, so let's say we draw another one, which is the draw, which is something like that, okay? Okay, so for example, this is a draw, right? So we give it a score 0, okay? Yeah, so these are called terminal states, yeah? Because it's the leaf. You know this is like a tree, yeah? We call it game tree, yeah? What's tree? Remember? Yeah, the game tree. We talk about binary tree, but here this is not binary anymore because look how many states for each kid. I mean, the maximum number of kids is 9, right? For the first layer we have 9 kids, 9 possibilities. So this is like a tree with at most 9 kids. The leaves, the terminal node is what? It could be the 9 slots occupied, or there's somebody is winning utility function, the end state. Yeah. So look, we give a score to each terminal leaves. So look, if let's say X is winning, agent is the maximize. So here, David, come on. This is very important. The X here x is looking for to maximize the values here. So let's say x is maximize, try to maximize. And the opponent here is try to minimize. Okay, so look, this node here, x is playing a field, right? So you will, as a agent, the agent would like to maximize, would get the maximum value of these three nodes. But here at this point, then the opponent is playing. Opponent is minimizing the values here. So look, I play one, I make a move. I need to choose the maximum value I can get from these states. And then now I choose one move, and then you, opponent, needs to play again. And you have a few choice, a few solutions, a few moves next, and you want to pick the minimum, right? So, do you get it? Two players, one is trying to maximize, the other one is trying to minimize, right? Because we're saying when agent is winning, we give a infinity score. When opponent is winning, we give a negative score. When it's a draw, we give a 0. Okay, so that's perfectly fit into this game tree, right? So at each layer, one is maximizing, the other one is minimizing. Okay, and then now we can let's say we can do this. Okay, and then you need to tell me the score. I draw a tree, and then you tell me what's the score. Okay, I only give the terminal value. Tell me the leaf value. Okay, let's say I have a node. Okay, let's just simplify a little bit. Okay, another one. Yeah, this is kind of like binary tree. Yeah. Okay. Okay, let's say 2, 3, 5, 6, 7, 1, 0, minus 5, minus 2, 3, 1, minus 5, minus 3. Okay, so now here I want to get the maximum here, and I want to get the minimum here. Okay, what's the minimum of 2 and 3?
2.
2. What's the minimum of 5 and 6?
5.
Okay. Now I'm here, I want to get the maximum of 2 and 5.
5.
Okay, you get it? 7, 1 minimum. 1. 0 and 5 minimum. Minus 5. Minus 2, 3, minus 2. 1 minus 3, minus 3. And then now 1 and minus 5 maximum. 1. Minus 2, minus 3, maximum. Minus 2. Okay, and then now I want to get the what's next? So this is to get the maximum. Okay. So this is to get the maximum of this now, and here I will be getting the minimum. Okay. So I probably need to draw one more layer. So I want to get the minimum here, which is minus 2. Okay. Yeah. Yeah. So in this way, the game tree who wins? Minus wins. Let's say this is 0. Let's draw. Okay. And then agent is this way. And then opponent is this way, and then it's minus 2. So it means that this game is more preferable to opponent. Okay, yeah, makes sense. Okay, this is like game tree. Okay, so we call it this tree. We call it MinMax tree, MinMax game tree. Right? Because look, yeah, one player takes the maximum value. The other player takes the minimum value, and the maximum value, minimum value, maximum value, minimum value, right? It's like the two players. Their target stands against each other. Their purpose is different. You want to go to the south, another one wants to go to the north. Yeah, that's the way it is. The agent wants to go to the right. The opponent wants to go to the left. The agent wants to go to the right. That's why he needs to look for the maximum value of the nodes. Yeah, and then the minimum wants to go to the left. So he will try to minimize the value. Okay. So look. Yeah, makes sense. Okay. Now we can implement this using the MinMax algorithm. Okay, and let's implement this. No, too noisy. Define MinMax. First of all, we have a cell function, and then state. We have a state. Can I please? So we have a depth. Okay, so the number of the depth of the tree, the game tree, and then we have which turn is it? Yeah, which turn is it? If it's trying to maximize or try to minimize. Okay. Now look, if cell dot is end, okay, we also have to pass the state, okay, game state, okay. If the cell is terminal, okay, somebody ends it here, state. Then we need to return the evaluation. This is the terminal loop, node. Now we need to give it a score, so we return the utility function. Yeah, remember, utility function of the state. Okay. That means that look, we are getting, yeah, this is the tree, game tree, and then as here, this is ended. This is the end state. Now we need to evaluate it, right? We need to evaluate. Remember, we talk about utility function. This is only applies to the end state. Okay, and then now look, we can do this. Then we can say if turn, yeah, if turn. Let's say if this is the maximize it, yeah. If this is the agent, we are trying to maximize it, yeah, maximize it. Then we have a score here. Score, we want to maximize it, so let's give it a minus infinity. Okay, minus infinity, max to infinity. Then we need to try for action in self the action. Remember, self the actions from the current state. So we are now doing the action, and we need to give a new state. Yeah, new state equals self dot success. Okay, self dot success with the current state. Yeah, and then look, this success function we talk about it. We given a state and we given an action, and it will give me a new state. Okay, and remember this function will return a copy of the state. Okay, so it doesn't modify this state. It will return a new state. Now we have a new state. Then I want to get a score, right? So I want to get a score. New score equal look here. Look, self dot MinMax. Okay, now this is recursion. Yeah, calling the tree. We talk about trees. One way to traverse a tree is to do the recursion. Yeah, MinMax. And then depth plus 1, right? So we have gone down one more level. And the turn would be minus 10, right? Because now, look, if 10 try to maximize, so minus 10 would be try to minimize. Yeah. And then the state would be new state. Alright. Look, there's a pitfall here. If you're trying to modify the original state, and here we need to revert the changes. But now we are we're retaining a new copy of the state. And here will be new score. And then new state. If the new score bigger than the score, right? We find the bigger score, then we try to replace it. Score equals new score. Right? And then after return, we can just return the score. Okay? Return the score. Okay, else, this is quite similar. Look, if 10, this is maximize, Eric. And here, what are we trying to do here? This block of code is trying to maximize. And what's here? What's here? What should I put here?
The opposite.
The opposite, try to minimize. We are trying to minimize here, so it will be the same. Score similar, yeah. Score instead of at the beginning minus infinity, we are giving the maximum infinity, yeah. Maximum infinity. And then look, this is the same. For act in self actions, then this is the same. But here, if new score needs to change, we need to change the sign. It's smaller than score equals new score and return score. Okay. MinMax function. We can actually separate this MinMax into two functions: find min and find max. So look, if 10 MinMax, then if this is maximized, so this will be minimized. So instead of the same function, we just minimize here, right? And then in the minimize, we change this here, call this function maximize. Make sense? Yeah. So now I'm writing everything inside this function. This function MinMax. Depending on the parameter 10. Right? When the 10 is agent, you try to maximize. When the 10 is opponent, you try to minimize. We can get rid of this 10 parameter and instead we can do what? We can call in the max function we call the min. In the min function we call the max. Okay. And then now look at this function return a score. We can add one more thing to return, which is the action. So which action takes you need to play? Which move? Which score you need to play? You need to play is to get a score. So we instead of returning a single function, right? Returning a single function, we can return the action as well as a tuple, right? Okay. Yeah. So if we implement this, the computer knows how to exhaust all the possible moves and then try to get a best move. That's why this is the game the computer is perfect at and we can't beat it. Right? As I said, because this game is so small. Like when you play at the beginning, yeah, you play using the left hand with the right hand. The best outcome we can get is a draw. Right? If you play this game against computer, the best result is a draw. Yeah? No matter who plays first. Yeah? Yeah? Because it's so small, right? As I said, 3 to the power of 9, right? This is so small. I can just exhaust it using this MinMax. Look, this is MinMax, yeah? So the computer will do what? Given a state, right? And then he can just exhaust it, search of possible moves. Yeah? Action is the like move. Possible move. And he finds the best move, right? Yeah? Because the maximum depth is 9, right? The maximum depth is 9, okay? Okay, so one other thing is what? If this is a chess game, right? Yeah? And this chess, the search space is so big, right? So how do you play a chess? How do we play a chess? We play a tic-tac-toe? Do we need to think about our opponent's move? Yeah? As I said, we think about it, yeah? If we think, okay, the opponent's move is next, and you will checkmate or you will find a three cross in a row, then we need to block it, right? That's the thinking. Yeah? The chess is the same. I play one, I make one move, you make one move, I make another one, you make another one. So that's the thinking, right? So but for the chess state, the search board is so big. So if you keep thinking, the search space, the tree is exponential, it grows exponential. You can't always finish all the searches, right? You can't finish it because it's so big. So in this case, we can set the max limit to the search. So we call it depth, DEPTH, depth limit search. We talked about that, mentioned that before, right? The depth limit search. What does it mean? Okay, so let's stop when the game tree is what? Is at say depth 6. Okay. So what does it mean? So I make one move, you make one move. I make another one, you make another one. I make another one, you make another one, and that's it. Stop. That's the argument will look no further because it's too far in the future, right? So I stop. I set a hard limit to stop at depth limit at 6. That will shorten the time to search, right? Do you understand? Because look, this tree maybe grow so big, you'll be spending time somewhere. Then if I set a hard limit, like okay, I'm stopping here and I don't care what happens in the future. Let's call depth limit search, right? Yeah, yeah. Any questions so far today? What have you learned today? Alright, Ryan. What's the keyword you can take away today?
It is.
Which one?
MinMax.
MinMax. What's MinMax? It's a what?
Tree.
It's a game tree. So one layer is trying to maximize it. The other one is trying to minimize it. Yeah. Okay, that will be it for today. Good job. Bye bye. You want to do some dancing? Bye bye.
Bye.
Bye bye. I can't see your face, Ryan.
Bye. Bye.
Eric, I can't see your face. Come on, stand up, please. Stand up, please.
Bye.
Okay, that's it. Bye bye.
It's long.